written, it's not separated. But as it is written, it's not separated. We can easily separate. We can bring everything with y on one side, everything with no y. X does. So I can write y prime divided by e minus y equal to x. Or, in other words, divided by 1 over 2 minus y equal to y. Now I can integrate both sides. Integral of 2 to y prime dx is integral of x dx. Notice that y prime dx is dy, so integral of dy is integral of x dx. Evaluate these integrals. E to the power y is equal to x squared divided by 2 plus a constant. Take logarithms on both sides. So y is 1 x squared over 2 plus a constant. So that's the whole question. One additional observation, besides the fact that this question itself is quite easy if you know how to separate variables in the differential equation. Second tip is, even if you do not remember this particular question, just try to plug in each one of these functions into the equation. Because number function e is not reasonable, you should expect a parameter in the general solution, so no constant there. The first four options, they are all reasonable from this perspective, so you can just try and plug in each one of these functions into the equation. If you plug in the first one, well, on the left hand side you're going to get just 2 divided by x. On the right side you'll get something which doesn't hold this constancy, so they cannot be. So option A is just not reasonable. But if you try option D, you plug it into the equation, you'll see that it just works. Okay, so questions about this equation? Alright, so ladies and gentlemen, talking about probabilities. I'll start with a reminder. We talked about random variables. And the random variable was something that measures a particular feature of an element. Let's say you toss a couple of coins and you measure how many heads you get. Or how many heads, what is the longest sequence of heads in a row. So something about the event. And we call it a random variable. With the random variable, the results associated with the probability density function. Or probability mass function. And that's just a function which assigns to the outcome x the probability that the random variable is in fact x. So it's just the probability of each possible outcome as far as the random variable is concerned. We also define expected value. It was on average each event, well, how much each event contributes to this random variable. So what is the value of this random variable average over many trials? And the expected value was defined with the following formula: sum last time we talked about a little bit about expected value of in some particular example. We thought that it's useful to know whether expected value of the lottery or some game is positive or negative for you. If it's positive, you should better play this game. If it's negative for you, you should better not play this game. So it's pretty important. So this time I'll start with defining new things. One is called variance. The other one is called standard deviation. So first, I'll talk a little bit about why define two other numbers besides the expected value. So expected value is not the only thing which matters. So if you have, I don't know, if you flip a coin and your random variable is 1, you get heads, and -1, you get tails. Well, if you keep tossing the coin, you should expect that on average the total amount of your, let's say you have such an experiment. You toss a coin, if it falls heads, you get $1. If it falls tails, you give away a coin. So the expected variable of the variable, which is +1 if you get heads and -1 if you get tails, is 0. So this probability will calculate at 1, this probability will calculate at -1, on average you get 0. So if you toss this coin many times, well, on average you'll get 0. You will not get more money than you started, not less. But of course, along the way, you do have some small loss or small win, depending on what is the actual sequence of outcomes. If it heads, tails, then you get 0, 1, 2, 3, 2, 1, 0. Or if it's the other way, tails, heads, well, then you get 0, -1, -2, -3, 2, -2, -1, 0. So even though on average or long term you're expecting to get 0, in between you will go with some part, some small wins, some small losses, and average out it will get you 0. Another experiment with the same average outcome. You toss a coin and you don't get anything. Neither win nor lose. So just keep tossing the coin. The average outcome is still the same, but the certainty, the outcome in between, grows. You know that whatever the result was in the coin, you'll always get 0. So one of these experiments is kind of more risky than the other. The range of outcomes is more spread out. So the game where you get $1 or lose $1 is a little bit more risky. So a measure of this kind of spread out of possible outcomes is this invariance. And it's defined by the following formula. It's sum over all outcomes of the following quantity. You take the sum of the difference between x and the average of all outcomes squared. And the sum is basically the probability. And mu is just the expected value of x. So let me explain what this variance is. Let me explain this formula. So first of all, mu, we call it that's just the expected value of x. It's the average of x over many trials. So the outcomes which are frequent will contribute more, outcomes which are not frequent will contribute much less. So this thing is a measure of how far your actual outcomes are on average from the mean. In other words, in fact, so this is called variance of x. You can write that variance of x is in fact the expected value of x minus mu squared. So it's on average how far is the square of the distance from the actual outcome and the average outcome. And then we also have the notion of standard deviation. This was about square of the distance. Standard deviation is about the actual distance. So suppose sigma of x is the square root of the variance. So let me give some examples. Let's say a variable which is always 0. If x is equal to 0 always, is equal to some number, constant. So if your variable just doesn't depend on the outcome of your event, like in this experiment where you toss a coin and it doesn't affect how much you, whether you get the dollar or not get the dollar, you always get the same amount, C. So in this case, the average outcome is still C. The expected value is C. It's basically C times 1. You get C with probability 1. There are no other outcomes. Variance. So what is it? It's the outcome minus the average squared multiplied by the probability, which is 1, 0. Because my outcome is always equal to the average. And standard deviation is also 0. So if the variable is not really random, if it is always the same thing, then the variance is 0. So let's discuss a little bit more meaningful example, something which captures what is randomness a little bit. My event will be flipping a coin 3 times. Random variable will be number of heads. Let's compute the probability distribution. The probability density function. The possible numbers of heads are 0, 1, 2, 3. If I have 3 coins, I can observe from 0 to 3 heads. I can get 0 heads only in one way, namely heads, tails, 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 and there are a total of 8 equally likely options. I can observe 2 outcomes for the first coin, 2 outcomes for the second one, 2 outcomes for the third one. A total of 2 times 2 times 2, which is 8. So here I have probability of 1 over 8. Similarly for 3 heads, same thing, probability 1 over 8. I can get it only in one way, heads, heads, heads. This one, if I want to get just one head, I can get it as head, tail, tail, or tail, head, tail, or tail, variance, standard deviation. Maybe before I compute the expected value, does anyone have a guess what the expected value will be? Yeah? 1. Why 1? So you compute just some probabilities. That's not the expected value. Some probabilities is always going to be 1. It's not an expected. The expected value is sum of outcomes multiplied by probabilities. So you get 0 1/8 of the time. So this contributes 0 times 1 over 8 to the average out. You get 1 3/8 of the time, so it contributes 1 times 0 over 8 to the average outcome. You get 2 3/8 of the time, so you get 2 times 0 over 8 contribution, and finally you get 3 1/8 of the time. Okay, so I can compute this. It happens to be 12 over 8, in other words 0 over 2. What I was trying to get is another heuristic and how to arrive at this 0 over 2. When you flip one coin, the expected value of the number of heads is 1/2. And how the dice get tails, how the dice get heads. On average, you get 1/2 heads. 1/2 head. If you flip 3 coins, well, each time you get an average 1/2 head. So for 3 coins, it should be 3 halves. And yes, we confirm here that this condition is actually correct. Okay, the variance. For variance, you don't get such a good intuition because basically we don't, intuitively understand what variance is. It's just one way to measure how spread out my variable is, how spread out the outcomes are. So just one definition, probability of getting 0 times 0 minus the average squared plus probability of getting 1 times 1 minus the average squared plus probability of getting 2 times 2 minus the average squared plus probability of getting 3 times 3 minus the average squared. And if you open the brackets and compute, turns out it's 3/4. And finally, the standard deviation is square root of 3/4 or square root of 3 divided by 2. So basically, these numbers, unlike the expected value, which is the average outcome, and it is quite an intuitive notion. These notions of standard deviation and variance are not that intuitive. I mean, if two random variables have the same mean, but one of them has much larger standard deviation, it means that the range of possible outcomes for this variable is much larger. You are more likely to get answers which are part of the average. But exactly what this number itself means, what is this square root of 3 divided by 2, well, not quite clear. But it is one of the standard ways to compare how spread out two different random variables are with respect to each other. So which one is more likely to get you an answer which is part of the average. Okay, so questions about this variance, standard deviation, expected value, density function of variables. So we talked about random may be what's called discrete, like number of years and a person lives. So it can be pretty large. We don't want to put a strict upper bound on the number of years, but still it's either 1, 2, 3, 4, up to some large number which we don't really want to bound. But some natural random variables actually not, the value is not a discrete set. It's not, the values are not separated initially from each other. For example, let's say height of a person. We can measure the height, well, as an actual number, not just rounded to the closest centimeter or closest millimeter. We can actually measure it. It's 183.0775. So if we have a really precise tool for measurement, we can get a very precise answer. And the height can be, well, basically any number. Or another example, let's say time until, so you come to a stop and the random variable which you want to measure is the time to the next bus. You don't want to round it up to the closest minute, you actually want to measure this time. And once again, it can be any number of, so whatever, any number of minutes. Could be 5.73 minutes, 5.7357 minutes. If you really know, if you really have a way of precisely measuring this thing, it's just a number. It's really not a finite number of possible outcomes. So when we have this situation, we talk about continuous variables. Continuous random variables. So this is a variable with infinitely many possible values. It is a bit more precise, would be to say not just infinitely many, but rather not discrete. They are not actually separated from each other. Better to see discrete. But for us, let's just pretend that it can be all possible numbers in some range. So let's say height is a random variable for which the range of numbers is the range of possible outcomes is all positive numbers. So height can be any positive. Still want to talk about probability of, say, a random person in this room having a particular height. The problem with this is, well, what does it actually mean to have a height which is exactly some number? What does it mean to have a height of precisely 183.7357 centimeters? Well, it's smallest meaningless. If we make the number too precise, the probability of getting exactly this number in the measurement is basically zero. So when the variable is continuous, we can't really talk about such a function. The probability of the variable being exactly on the nodes some number. But we can talk about what's called a cumulative distribution function. And that's, by definition, the probability of this variable to be smaller than some number. That is noted by capital F of x. So what the question of what is the probability of a random person in this room having a height 183.73257 centimeters is almost meaningless. the question of what is the probability of random person in this room having a height of at most 183.7 centimeters is quite limited. We can take all the people in this room, measure their heights, count the number of people whom their height is at most 183 point something centimeters, divide by the total number of people, and we get the sense. So this kind of function is mean. It measures probability of your variable being at most some number. So let's talk about this function. What kind of properties does it have? So properties. One property, it's always increasing. So if you increase x, the probability that you get x smaller equal than x is going to increase. So you get, of course, the probability of somebody, of the random person in this room having a height at most 150 centimeters is smaller than a random person having a height of at most 180 centimeters. Just because every person who has a height at most 150 also has a height at most 180. So f of x is increasing. Another property, well, every person in this room has some type. How can we express this in terms of this function? If we measure the probability that a given person has height at most some really, really huge number, this should be equal to 1. The way we write this mathematically is that if we measure that this person has height at most some large number and make this large number go to infinity, this should be 1. And also another property as you make your variable smaller and smaller, more and more negative, the probability that you get an outcome which is really, really large and negative should be close to 0. Every outcome is some number, and the number currently is smaller than the many numbers which go to minus infinity. So such a function, oh yes, and of course its probability, so it is always from 1 to 0. So we know that some function is a cumulative distribution function for a random variable is to look at its graph and make sure that it looks somewhat like this. It is close to 0 at negative infinity, close to 1 at positive infinity, and increases in between. So these are the important features of a cumulative distribution function. It should be increasing from about 0 to about 1, and the rate of increase can be different things. So let's talk about an example. So I gave you a random variable. It's the following thing. Your experiment, your event is arriving at the train station at 3 a.m. and waiting for the next train. What you measure, your random variable, is how much time you wait at the station. And here's all the information you basically need to know about this variable. It's the cumulative distribution function. So what I want to show in this example is how to answer some simple questions about this experiment. So for example, what is the probability of waiting at most 1 hour? Second question, same question, but now from 1 to 2 hours. Third question, same question, but now more than 2 hours. So first of all, this function is, has a little bit strange formula. It's 0 when x is negative. It's given by some formula when x is positive. In this case, it's quite natural for this function to be 0 when x is negative. Because what does it mean? X being negative is that you arrive at the station and then wait for a negative amount of time. It's meaningless. So the probability that you measure a negative amount of time is 0. That's what the 0 stands for. Okay, so let's solve the actual questions. First question is basically, it's on the notes what this function is about. It's exactly what it is about. It's the probability that my random variable is at most 1. So probability that my random variable is at most 1, that I wait at most 1 hour, is just the value of my function at the point 1. And all I have to do is plug in the point 1. So 1 is positive, I plug it into the second formula. 1 minus 2 and it's about 0.26. So it tells you that with this cumulative distribution function, if you keep repeating this experiment, if you keep arriving at the same train station at 3 a.m., about a quarter of the times you'll wait less than 1 hour. Okay, second question. What's the probability of waiting anywhere between 1 hour and 2 hours? How can I find this probability using my cumulative distribution function? Okay, so if I plug in 2, I'm going to get the probability that I wait at most 2 hours. It would be half hour, 1 hour and a half. Half hour is not good. I want to measure only the outcomes when the time to wait is between 1 hour and 2 hours. So this is more than enough. This captures all the events where I wait most 2 hours, including the events where I wait most 1 hour. Exactly, yes. So if I want to measure the probability that my variables from 1 to 2, what I'll do is measure the probability that it's at most 2, so what proportion of events where I wait most 1 hour. What I get, the difference is a proportion of events where the wait time was between 1 hour and 2 hours. Okay, now we just plug in. So it's 1 minus 2 minus 1. And this is approximately 0.2. So for this one, this tells you that if you keep repeating this experiment over and over, about a third of the times, you'll wait between 1 hour and 2 hours. So questions about this one? Yeah. In this forecast, maybe over the rate is right. Other questions? Okay. And finally, what's the probability of waiting more than 2 hours? Yeah? Subtract these two numbers from what? From 1, yes. So, 2 ways to solve this question. Either use the solution to these 2 parts. So, we know that the wait for some amount of time is going to be either smaller than 1 hour, or between 1 hour and 2 hours, or more than 2 hours. So we can say that it is 1 minus whatever it was, 0.3, which is 0.41. So that's one solution. Another solution would be, well, what's the probability of waiting more than 2 hours? Well, I'll wait either more than 2 hours or less than 2 hours. Probability of waiting less than 2 hours is f of 2. So, alternatively, it can be written as 1 minus the probability of waiting less than 2 hours. So if you want to get this answer without doing these 2 steps, well, here it is. 1 minus the value of the function in the point. And not surprisingly, you should get the same answer. So if you know this cumulative distribution function, you can answer quite a lot of questions. If you have a cumulative distribution function for the height of in this room, well, you can answer questions like how many people here are from 170 centimeters to 190 centimeters? How many people are lower than 160 centimeters? How many people are lower than 2 meters? And so on and so on. So all the reasonable questions which you can ask about this variable can be answered just from this cumulative distribution function. Okay, so this is the concept of cumulative distribution function. Maybe let's take 10 minutes break right now, and then we'll talk about